Hello everyone, and welcome to the new episode of our series of solving daily LeetCode challenges. And today we are going to solve a problem called minimum size subarray sum, which is classified as medium, and I think it's an appropriate difficulty for this problem. And without further ado, let's move to the problem statement. We are given an array of positive integer nums. It's very important that the integers are positive. And we also have a positive value target. We need to return the minimal length of a subarray whose sum is greater than or equal to target. And if there is no such subarray, we should return 0. And in our examples, in the first example, the answer is 2 because we have this subarray of length 2 with the sum exactly 7. And here the answer is 1 because here target is 4 and we can choose any of those 4s. And here the answer is 0 because there is no way for us to find a subarray with sum greater than or equal to 11, since this sum of this array is equal to 8. Okay, cool. And basically, they also have a follow-up which says if you have figured out a linear solution, try coding another solution with time complexity of big O of n times logarithm of n. And in this video, we are going to discuss the ideas for both of these solutions, for linear one and for n times logarithmic of n. Let's start probably from the linear one. And to solve this problem with the linear complexity, we will need to use a well-known technique called two-pointers. So what's the general idea of the solution? We want to iterate through all of the possible left bounds of our subarray. And there are n such left bounds. We will calculate the answer for each of them, and we will choose the optimal one among them. And by the answer for each of them, I mean the following. Suppose we have some fixed left bound of our subarray. We want to find the smallest possible right bound, such that sum from left bound to right bound is bigger than or equal to target. And so this means that nums of left bound plus nums of left bound plus 1, and so on up to nums of right bound is bigger than or equal to target. Okay, cool. So we have the general idea. Now let's try to think how to implement it optimally. And here is where two-pointers technique comes handy. So suppose that we know the answer, this right bound, for some left bound 1. And this answer is equal to right bound 1. Okay? So let's assume that we have some other value, left bound 2, which is equal to left bound 1 plus 1. Basically, we are shifting the left bound of our subarray to 1. Then I say that right bound 2 always greater than or equal to right bound 1. And the intuition for that is that when we shift the left bound to the right, we make our subarray smaller. And since all of the values in our nums array are positive, we need to either do not move right bound of the subarray, or we need to move it in the direction of increasing the length of the subarray. Because, by moving our left bound, by making our subarray smaller, we also made the sum smaller. And now it is possible that it is no longer greater than the target. And therefore, we need to increase it. Okay, that was the intuition. I will also give a formal proof. If you don't like proofs, you can just skip through this chapter and go to the next time code. So right now I will show you the proof. Okay, so suppose that the optimal answer for left bound 1 is right bound 1. This means, I'll remind you that right bound 1 is the smallest possible index, such as the sum from left bound 1 to right bound 1 is greater than or equal to target. Now let's assume that we have left bound 2, which is equal to left bound 1 plus 1. And suppose that the optimal answer for left bound 2 is right bound 2. So yeah, nothing new up to this stage. Our statement is that right bound 2 is greater than or equal to right bound 1. And let's prove it by contradiction. Suppose that the opposite is true. Suppose that right bound 2 is actually smaller than right bound 1. This means that, yeah, we remember that sum from left bound 2 to right bound 2 should be greater than or equal to the target, because right bound 2 is the answer for left bound 2, which is equivalent to sum of left bound 1 plus 1 to right bound is greater than or equal to the target. And we need to remember that the numbers in our array are positive, and this in turn means that sum from left bound 1 to right bound 2 is greater than the target, because yeah, now we made our subarray bigger and therefore our sum increased. But our initial statement was that the optimal answer for left bound 1 is right bound 1, and since right bound 2 is smaller than right bound 1, then we have a contradiction, and therefore it's never possible for right bound 2 to be smaller than right bound 1. Okay, so that's the end of the formal proof of this two pointers technique. Now let's look at the code for the solution. The code is quite short, I would say, and elegant. So we iterate through all of the possible left bounds, and we have some variables for right bound and for sum. And yeah, we will increase right bound until we either reach the end of the array or our sum become greater than or equal to the target. And we will check if the sum that we've achieved is greater than or equal to the target, then we possibly will update the result for this left bound. Because yeah, it's possible that sum will be less than a target, for example, if we've reached the end of the array with our right bound. Okay, and now when we will move from left bound to left bound plus 1, we need to decrease the sum by the value of nums of left bound. And yeah, if we have never found the result by our problem statement, we are supposed to return 0. So yeah, we will reassign the variable to 0, and we will return the resulting variable. The complexity of this solution is big O of n, which might be not intuitive, because we have a loop inside another loop. But let's see. So our left bound variable, it has exactly n states, where n is the length of the array nums, because yeah, it travels from 0 to n minus 1. And our right bound variable, it also has exactly n states. And my point is that this this loop, this while loop, will execute n times in total. So our aggregate number of operations in this loop will always be equal to n. So yeah, for some left bound, we might do a lot of operations inside of this loop, but for other left bounds, we will do not so many operations, and in the end, this right bound will travel exactly, not even exactly, but not more than n steps. And because of that, the complexity is big O of n. Okay, so let's now move to our follow-up. And the follow-up says, can we come up with solution with n times logarithmic of n complexity? And yes, we can. so binary search comes to the rescue. Once again, we want to iterate through all of the possible left bounds of our subarray and find the answer for each of them and choose the optimal answer among them. So we can find this right bound of the array for a fixed left bound with binary search. Why is that? Let's look how our sums will look like. So they will be equal to nums of left bound 1 plus, some errors are in here, but now are fixed. So our sums will look like this. And since the numbers in our array nums are positive, which is super important, this array will actually, this sequence of sums will actually be sorted in increasing order. And we need to find the first value in this sequence such that this number is greater than or equal to target. And this is a classical binary search problem. Okay, so let's take a look at how this is implemented by me. Okay, so for now, let's forget about this partial sum part. I will explain it a little bit later. So what we are doing here, we are iterating through all of the possible left bounds, and we are trying to find the minimum length of subarray starting at this left bound with the sum greater than or equal to target. And yeah, we are comparing this value with our current result, and we are choosing minimum. Okay, how do we find this length of the subarray? We do it with binary search. So we define the left bound of our binary search, right bound, and then we do the classic binary search. We find the middle, and then we check if the sum from the left bound to middle is greater than or equal to target, then we found the potential answer, but we actually can look for a more optimal one, so basically for a subarray with smaller lengths. And if the sum is actually smaller than target, then we need to increase the size of our subarray, and because of that we move the left bound of our binary search. Okay, so the only untold part of this solution is how do we calculate sum? And now we have to return to our partial sums concept. So what is partial sums? Suppose we have an array of nums, and let's define partial sums for some index I as the sum of all values in nums up to I inclusive. So basically, partial sums of 0 is equal, okay, I will show it in here, I guess. Partial sums of 0 is equal to nums 0. Partial sums of 1 is equal to nums 0 plus nums of 1. Partial sums of 2 is equal to nums 0 plus nums of 1 plus nums of 2, and so on and so on. How does this array help us? Suppose we want to find a sum of some subarray in our array nums. Suppose we want to find a sum of subarray that starts in index L and ends in index R. I'm stating that sum from L to R is equal to partial sums of R minus partial sums of L minus 1. And why is that? Let's take a look at what is the partial sums of L minus 1. It's nums 0 plus nums 1 plus dot 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 plus nums L minus 1. What is partial sums of R? It's the same sum of nums 0 plus nums 1 plus dot 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 plus nums of L minus 1. Then we also add nums L. Then we add nums L plus 1, and so on. And in the end, we are adding nums R. And actually, our sum from L to R is actually equal to this sum, right? So when we will substitute partial sums of R minus partial sums of L minus 1, this part will cancel out, and we will only be left with this part that we are actually interested in. And that's why it works, and this is exactly what I implemented here. I've said that partial sums of 0 is equal num 0, and then for all the other values, partial sums of I is equal to partial sum of I minus 1 plus our current value. And then when I calculate the sum, I do this magic of substituting partial sum of R minus partial sum of L minus 1. In our actual code, yeah, I also decrease the right bound as well, but that's only because in my binary search, right bound is not inclusive but exclusive. So yeah. Okay, so that was the second solution, the binary search solution. What lessons for a real technical interview can we get from these tasks? There are several lessons. First of them is you should always clarify your assumptions and ask about constraints, because, for example, for this problem, it was vitally important that all of the numbers in the array of nums are positive, and it might not always be the case. And the second lesson is I would suggest for you to, if you have several solutions in mind, do not hesitate to tell it to your interviewer. You can tell, okay, I can solve this problem in several ways. First of all, there is a trivial solution when I just iterate through all of the possible subarrays and calculate the sum for each of them. Then there is this two-pointer solution, and it goes like this. Then there is this binary search solution, and it goes like this. Because by doing that, you will show your interviewer that you know a lot of stuff, and you will make a really, really good impression. Okay, guys, so thank you very much for listening. This video was kind of a long one, but I think it was a fun one because we basically went through two completely different solutions that might help you in your future and in your coding interviews. And yeah, hope you learn some new things, guys. So yeah, thank you very much for your attention. Press like, subscribe, and I'll see you soon. Bye bye.